Hello friends, welcome back to my channel. I hope you all are fine, and I also hope you must have seen my previous two videos on distillation. In the first one I have discussed uh, fundamentals of distillation, and in the second one I have discussed material balance for distillation. For those of you who have not yet seen those videos, I am giving links to those videos in the description section. ठीक है. Now this will be part 3, third part of my lecture series on distillation, and I'll be talking about vapor liquid equilibrium in it. I'll be discussing the importance of vapor liquid equilibrium in distillation and how you can represent vapor liquid equilibrium in various ways. So let us start the discussion. So title for this is distillation part 3, and we are going to discuss vapor liquid equilibrium. For vapor liquid equilibrium, this will be the first lecture, and in coming another 3 or 4 lectures, I'll be talking about vapor liquid equilibrium. So let us start the discussion. Vapor liquid equilibrium, or simply VLE, V vapor L liquid equilibrium. Let us understand why it is important to have knowledge about vapor liquid equilibrium in distillation. So when distillation is carried out, that is in distillation, vapor and liquid phases, they are in contact with each other. Vapor and liquid phases, they come in contact with each other. How the contact is established, let us understand. You know, in this operation, feed is a liquid solution, and this liquid solution is boiled to create the vapor phase, and then vapor phase is condensed to get the distillate. Okay, so let us understand. Vapor phase is created from the original liquid solution. Original liquid solution, that is feed liquid solution, is boiled and the vapor phase is created from it. Then, in order to increase degree of separation, or in other words, in order to increase purity of distillate and bottom product, what is done? Repetitive condensation and vaporization is done. There is repetitive condensation of vapor phase, and there is repetitive vaporization of the liquid phase, or you can say repetitive boiling of the liquid phase. Due to this, vapor and liquid phases, they come in contact with each other, or they continuously remain in contact with each other. So we will understand this with the help of this diagram, schematic diagram. I have discussed this in my first lecture. Okay, so this is representing continuous distillation operation. So feed solution is continuously admitted to the column. It flows down. It flows down to the reboiler. It is boiled in the reboiler. Resulting vapor phase is admitted to the column at the bottom. The vapor phase rises through the column, and then it is taken out from the top. Then it is sent to the condenser. It is condensed. Resulting condensate is divided into two parts. One part is sent back to the column as reflux, while the other part is taken continuously removed as distillate. And at the bottom product is from the reboiler. Bottom product is continuously removed. Okay, so within the reboiler there is continuous vaporization or continuous boiling of liquid solution, and within the condenser there is continuous condensation of the vapor phase. So this the the reflux that comes in the column, it flows down, gets added to the liquid solution, feed solution, and again it is sent again it goes to the reboiler where boiling takes place. So you can see within the column, liquid phase and vapor phase, they remain in contact with each other. They remain in contact with each other. So this is happening due to repetitive condensation and vaporization, which is done to enhance separation, to increase the degree of separation, to increase purity of top product and bottom product. Okay. So due to this, liquid and vapor phases, they remain in contact with each other. During this contact, during the contact, what happens? Components get transferred between them. There is transfer of components between vapor phase and liquid phase. We will go into details of this transfer in our coming lectures. For time being, let us understand whenever these two phases come in contact with each other in the column, mass transfer occurs between them. That is, components gets transferred between them. Now this transfer, in order to have successful distillation, this transfer is important. We need to have this transfer going on. But this transfer will continue as long as these phases, that is vapor and liquid phases, they are not in equilibrium with each other. So as long as they are not in equilibrium with each other, mass transfer will occur between them. As soon as they come in equilibrium, mass transfer will stop and there will be no successful distillation. Okay. So point is, for successful distillation, we need those two phases to be away from equilibrium. Okay. So how equilibrium is reached, it is important to understand how quickly or what time is required to attain equilibrium state and how it is achieved, how it is reached. It is important to understand this, and that's why I'm saying VLE plays a critical role in distillation, and that is why it is important to have knowledge about VLE. If you are dealing with any system, for example methanol water, and if you want to separate these two, so feed will be methanol water solution, and if we want to design or if you want to carry out successful distillation of this solution, we need to understand vapor liquid equilibrium for methanol water system. Okay, so in short, VLE plays a critical role in distillation, and that is why we have this in our discussion. Okay, VLE, knowledge about VLE helps us in design of equipments for distillation. It is necessary in the design of equipments for distillation, and that is why we are understanding VLE in our discussion. Okay, so this tells us why vapor liquid equilibrium, that is VLE, is important in distillation. Okay, let us move ahead. Now, in order to understand, we will understand VLE for a binary mixture of two components. Which are these components? One is component A and component B. Again, in this binary mixture, A is the more volatile component. When I say A is more volatile component, then what is true? Boiling point of A is less than B. Therefore, A will vaporize first, and at a given temperature, the vapor pressure of A is more than B. Okay, so when A is the more volatile component, then this is true. This three statements are true. First is boiling point of A is less than B. You already know this. Then A will vaporize first. This is very simple to understand. And important thing to note is, at a given temperature, vapor pressure of A is more than that of B. Okay. Now let us understand the concept of VLE in under two categories. The concept of VLE is understood for, first we will understand it for pure A and pure B, and then we will understand for the binary mixture of these two components. So first we will be discussing VLE in case of pure components, pure substance. VLE for pure A and pure B. So what we will do, we will discuss VLE for pure A, and similar discussion applies for pure B. So we will just discuss how VLE for pure A, and for pure B a similar discussion will be applicable. Okay. So for pure components, VLE is relation between, if you have pure components, then vapor liquid equilibrium is nothing but a relation between vapor pressures of that component and corresponding temperatures. How vapor pressure of that component depends on temperature. Vapor pressure is a strong function of temperature. It changes with temperature, and how it changes is nothing but vapor liquid equilibrium. Okay, the equilibrium curve, in order to represent VLE, we can plot the equilibrium curve. And how is this plotted? The equilibrium curve is obtained by plotting vapor pressures on y-axis and corresponding temperatures on x-axis. So when you plot vapor pressures of a component on the y-axis and corresponding temperatures on the x-axis, you get one curve. That curve is equilibrium curve. And for pure components, it will be vapor pressure curve. So for example, we are going to discuss vapor pressure curve for pure A. So for example, vapor pressure curve of pure A is shown over here. And this curve for pure A, it extends from the critical point of A, that is Ca, to its triple point, TPA, triple point of A. Okay. So critical point, at critical point, temperature and pressure are critical, whereas a triple point is that point at which all the three phases, solid, liquid and vapor, they coexist. Okay. So we are saying that vapor pressure curve for pure A is extending from its critical point to its triple point. So let us see over here. So on, you have pressure plotted on y-axis and temperature plotted on x-axis, and you get the curve. We are saying that the curve is extending from critical point of A to its triple point of A. Okay, but I have not shown the dynamics of solid phase in this diagram. The reason is, in distillation solid phase is not involved, so we have neglected dynamics of solid phase over here. The dynamics of solid phase are not shown. The reason is solid phase is not involved in distillation. Now, when you have this curve, the vapor pressure curve or equilibrium curve, every point on the curve gives a relation between vapor pressure of A and the corresponding temperature. You choose any point on the curve. Okay, so for example, this point. So this point will give vapor pressure at the corresponding temperature. Vapor pressure and the corresponding temperature. Any point, you choose any point. For example, at this point, you will get vapor pressure and you will get corresponding temperature. Okay, so this is how VLE can be represented or is represented for pure components. Over here, we have shown it for pure A. Okay, let us move ahead. Now, again, I'm showing the same curve. So you have pressure plotted on y-axis, temperature plotted on x-axis, and you have the curve that extends from critical point of A to the triple point of A. The curve extends from critical point to triple point of A. Again, we are not showing the dynamics of solid phase. Okay. Now, if you look at the diagram, if you look at the plot area, you can see that this curve, the vapor pressure curve for A, is dividing the plot area into two regions. Which are this region? One region represents the liquid phase, while the other region represents the vapor phase. So that's why we are saying the curve divides the plot area into liquid and vapor regions. So region above the curve is the liquid region, whereas the region below the curve is vapor region. Every point on the curve, I have already talked about it, every point on the curve gives vapor pressure at that temperature. You choose any point. So you choose any temperature, you go to the curve and you go to the pressure axis, you will get vapor pressure at that temperature. The other understanding is every point on the curve gives boiling point at that pressure. Okay, so you choose any value of pressure, go to the curve and then come to the temperature axis, you will get corresponding boiling point. Okay, then one more thing is every point on the curve represents a two-phase mixture. At every point on the curve, there is coexistence of vapor and liquid phases. The two phases are coexisting. There is a two-phase mixture, and that's why this vapor and liquid, they are in equilibrium with each other. They coexist and therefore they are in equilibrium with each other. Okay. So every point on the curve is representing such a two-phase mixture. Okay, let us move ahead. Now, the temperature corresponding to 1 atmosphere, if you choose 1 atmosphere pressure on the pressure axis and try to and move to the curve and then go to the temperature axis, the temperature that you get for this pressure is nothing but normal boiling point of heat, Tn. Okay, so the temperature corresponding to pressure of 1 atmosphere, temperature corresponding to atmospheric pressure is the normal boiling point of heat. Okay, so at 1 atmosphere, if I go to the curve and then come to the temperature axis, the temperature that I read is normal boiling point of heat. Okay, then as I have already said, Ca is the critical point. Ca is the critical point. What are the coordinates of this critical point? Coordinates are Tca and Pca. So pressure is Pca and temperature is Tca. And these are critical temperature and pressure. Tca is the critical temperature and Pca is the critical pressure. We will shortly understand significance of these two, critical temperature and critical pressure. Okay, now let us move. Now vapor transforms into a gas above Tca. Vapor transforms into a gas above Tca. If temperature of the gas is above its critical value, then vapor transforms into a gas. So there will vapor will no longer exist. It will get transformed into gas. If temperature is above Tca, and if you try to liquefy a gas, you will not be able to liquefy it. You will not be able to liquefy it no matter how high pressure you apply. Okay. So the point is, if temperature is above Tca, A cannot be liquefied. A cannot be liquefied no matter how high is the pressure. In order to cause liquefaction, temperature has to be below the critical temperature. Okay. So a similar this this is how we can discuss vapor pressure curve or equilibrium curve for pure air. Okay. A similar discussion can be done for pure B. A similar vapor pressure curve exists for B. Okay. So I have already shown uh, this. At 1 atmosphere, you have normal boiling point, and then critical pressure, critical temperature, significance of critical temperature. If the temperature is above its critical value, above the critical temperature, A cannot be liquefied, no matter how high is the pressure. Okay. A similar vapor pressure curve exists for B. So for B, you will have again a curve that will extend from its critical point to its triple point. It will have its critical temperature, critical pressure. Same similar discussion can be done for vapor pressure curve of pure B. Okay, so that ends our discussion on VLE for pure components. We have discussed it for pure A, and corresponding discussion applies for any other pure component. Okay, now let us discuss VLE for binary mixture. VLE for the binary mixture. For the binary mixture, VLE is a relation between, for pure component it was simply relation between vapor pressure and temperature. But for binary mixture, VLE is a relation between temperature, pressure and concentration. Concentration of the more volatile component. Okay, so we have to represent relationship between three parameters: temperature, pressure and concentration. Okay, thus to describe VLE, we need three variables. Which are these three variables? We have already noted those variables: temperature, pressure and concentration. Okay. Now for concentration, mole fraction is the convenient unit for expressing the concentration, and we are going to use it. Mole fraction is the convenient unit for expressing concentration. So with three variables involved, temperature, pressure and mole fraction, a three-dimensional plot is required to represent the VLE. You cannot represent it on ordinary two-dimensional plot. We need three-dimensional plot. Why three-dimensional plot? Because there are three variables involved. The plot has the following three axes. So one will be pressure axis, other one will be temperature axis, and the third one will be concentration axis. On concentration axis, mole fraction is plotted. Okay, now let us understand it in detail. Uh, See, there are three axes: pressure axis, mole fraction axis, and the temperature axis. Okay, now vapor pressure curve for pure B. Let us first talk about pure B. So pure B, when you have, there is a binary mixture as we said in the beginning. It contains two components. So if you have mole fraction of one component, you can easily get mole fraction of the other component, because sum of mole fractions is 1 and there are only two components. So why I'm telling this? I'm telling this because vapor pressure curve for pure B will lie in x is equal to 0 plane. X is equal to 0 plane. Now what does x is equal to 0 plane represent? X is equal to 0 means you already know small x is mole fraction of more volatile component in the liquid phase, and over here more volatile component is A. So if x is 0, there is no A. If x is 0, there is no A, and you have pure B. And that's why in x is equal to 0 plane, every point will represent pure B. Every point will give property of pure B. Okay. So this is this plane. You can see pressure and temperature. This plane. This is x is equal to 0 plane. So it is representing pure B, and that's why vapor pressure curve for pure B will lie in that plane. And as usual, it will extend from its critical point CB to its triple point. CB is the critical point of pure B, and TPB is the triple point of pure B. So you have this curve. The curve is extending from critical point CB to TPB, triple point of B. So this green curve which is lying in x is equal to 0 plane, this is nothing but vapor pressure curve for pure B. Okay, now let us move. Then vapor pressure curve for pure A. Now you can easily guess where it will lie. Vapor pressure curve for pure A, it will lie in x is equal to 1 plane. X is equal to 1. Mole fraction of A is 1. That means it is pure A. Therefore, vapor pressure for pure A, it will lie in x is equal to 1 plane. Further, it will extend from critical point of A to triple point of A. CA is the critical point for pure A, and TPA is the critical triple point of pure A. Okay. Now let us first represent this plane. X is equal to 0, x is equal to 1 plane. X is equal to 1 plane will be this plane. X is equal to 1 plane will be this plane. And vapor pressure curve for pure A will lie in this plane. It will extend from the critical point CA to triple point of pure A. So this blue curve which is lying in x is equal to 1 plane, it is nothing but vapor pressure curve for pure A. Okay. Now we have region that lies between these two planes. Region that lies between x is equal to 0 plane and x is equal to 1 plane. Okay. Now let us area between x is equal to 0 and x is equal to 1 planes, that has this area has regions, two regions that represent liquid and vapor phases. So you have liquid region, you have vapor region within the area that is lying between the two planes. Now within this area, liquid region and vapor region, they are separated by a double surface. Unlike for pure components where vapor and liquid regions were separated by a curve, in this case for binary mixture, liquid and vapor regions, they are separated by a double surface. And what can we say about this double surface? This double surface extends from a vapor pressure curve of A to that of B. So you have double surface over here lying between these two planes, and that is extending from vapor pressure curve of pure A to vapor pressure curve of pure B, or the other way. It extends from vapor pressure curve of pure B to the vapor pressure curve of pure A. Okay. So I hope this is clear to you. But within the two planes, between two planes, area between the two planes, which two planes, x is equal to 0 plane and x is equal to 1 plane. This area has two regions. One region represents liquid phase, while the other region represents vapor phase. Okay. And there is a double surface that separates these two regions. And that double surface, it extends from vapor pressure curve of pure A to that of pure B. Okay. Now let us go into details of this. The VLE is better. Now it is clear. VLE, if you have to represent VLE, we need this three-dimensional plot. We need to understand a double surface. Okay. In order to, so it is a kind of complicated, you can say, discussion. It would be a complicated thing to discuss really with this three-dimensional plot, and that's why we can understand vapor liquid equilibrium in a better way if you are studying it at a constant temperature or at a constant pressure. So if you are studying VLE at constant temperature, you have constant temperature equilibrium. And if you are studying it at constant pressure, you have constant pressure equilibrium. So what is done for this? If you have to study it at constant temperature or constant pressure, what is done? For this, the double surface that exists between the two planes and which separates liquid and vapor region, this double surface, you cut it by a constant temperature plane. If you cut it by a constant temperature plane, the resulting, you can say, surface will give VLE at constant temperature. Okay. Cut by a constant temperature plane, and in order to study it at constant pressure, you can cut it by a constant pressure plane. So we'll understand it. Now this red plane shown with red edges, it is parallel to pressure axis, and therefore it is a constant temperature plane. It is a constant temperature plane. So I have used constant temperature plane to cut the double surface that is lying within it, the double surface that is lying between the two planes. Okay. And then by using constant pressure plane, this plane is parallel to the temperature axis, and therefore it is constant pressure plane. So if you cut the double surface by constant pressure plane, you will get constant pressure. You can study really at constant pressure. Okay. So now let us understand it detail. The constant pressure plane, this thing. So if you are using the constant pressure plane to cut the double surface, what happens? This plane, as it intersects with the double surface, what does it do? It gives a loop curve. The constant pressure plane intersects with the double surface to give a loop curve. What is this loop curve? This is a loop curve without any maxima or minima. And this loop curve, the loop curve that is obtained in the process, it extends from boiling point of B to boiling point of A. It extends from TB, which is boiling point of B, to TA, boiling point of A. Okay. So I have already told TA is boiling point of A and TB is boiling point of B. Now I will show you the surface. This I will show you the loop curve. This is the loop curve. This loop curve is obtained through intersection of constant pressure plane with the double surface. And what is the significance of this loop curve? This loop curve does not have any maxima or minima, and it is extending from boiling point of pure B to boiling point of pure A. Same thing happens with the constant temperature plane. Let us understand. The constant temperature plane will intersect with the double surface, and it intersects with the double surface. It also gives, the intersection also results in a loop curve. Again, this loop curve is without any maxima or minima, and this loop curve with constant temperature plane, the resulting loop curve extends from PB naught, which is vapor pressure of pure B, to PA naught, which is vapor pressure of pure A at this temperature. Okay, so PA naught is vapor pressure of A and PB naught is vapor pressure of B. Okay, so when you have these two loop curves, that is loop curve obtained at constant temperature, it is constant temperature equilibria, and it is very easy to understand that. And when you have loop curve obtained through intersection of constant pressure plane with the double surface, that will represent constant pressure equilibrium. Again, that is very easy to understand. Instead of uh, discussing the three-dimensional plot, it is better to study the loop curves. So we have constant temperature equilibria and constant pressure equilibria. Okay, so with this I end my discussion for this lecture. We will continue with this. Before that, let me show you the loop curve. Okay, the loop curve obtained using constant temperature plane. We have said that it extends from PB naught, vapor pressure of pure B, to vapor pressure of pure A. Okay, so in my coming lecture, I'll be talking about these two equilibria: constant temperature equilibria and constant pressure equilibria. Okay, so with this, I end my discussion for today's lecture. You please subscribe to my channel. You hit the bell icon so that you will get notified as soon as I upload a new video. For today, thank you for being with me. Bye.